Hello, everybody. I would like to present you my poster. The title is The Optimal Investment Strategies Under the Relative Performance in Jump-Diffusion Markets. This is a joint work with Morgan Stephenson in the University of Copenhagen. So I start with the introduction. So first of all, I would like to define our problem. The problem is to determine the optimal investment strategies for an agent and for a large group of agents where they have the power utilities under the relative performance concerns. Okay, so we find the optimal strategies for this representative agent. So we saw a classical Merton problem to determine the optimal strategies under the relative performance, and we consider different cases actually. And our work is actually an extension and a special case of the paper of Lecker and Zaripov. So first of all, we define the model. We are working on a classical probability space. And in the followings, we define the dynamics for the agent and for the groups. Here, we call pi and pi hat the allocations for this agent and for the groups. So we are trying to optimize these proportional allocations. So let X and Y denote the wealth of the agent and the group. And they have the following dynamics here. So here, mu and mu hat are the constant drift parameters. Mu, sigma, and sigma hat are the constant volatility parameters, and we have the constant jump sizes, which are the epsilon, epsilon tilde, and epsilon hat. And here, W and B are the independent standard linear processes, where W is idiosyncratic noise and B is the common noise. And we have two Poisson processes which denote the jumps in the wells. So where N and tilde are these Poisson processes with the constant intensities lambda and lambda tilde. Okay, so here is the optimal control problem for the agent. So we work with stochastic optimal control problem, which is defined by 2. Okay, so we are optimizing pi here, and we use this utility function. Okay, and given these initial conditions here, okay, here lambda is the risk aversion of the agent, theta is the relative performance parameter, okay, and this is defined on the given admissible strategies. Next, we write the corresponding Hamilton-Jacobi-Bellman equation as given here. We also have the corresponding jump terms in the supremum term in the Hamilton-Jacobi-Bellman equation, and using some suitable answers here, which is given here, we find this equation. Okay, so from here we are trying to isolate optimal pi, which is the optimal proportion for the agent, but this is a nonlinear equation, so we cannot directly isolate optimal pi. Therefore, we consider the following special cases. First of all, we consider pure diffusion model where epsilon and epsilon tilde in this equation are 0. And then we find the optimal strategy as given by 5. So next, we consider a single Stokes case. For this, we need to have these following conditions here. And then we have the following optimal strategy for the single Stokes case here. Okay, and then we give some results for these single Stokes cases here, and actually these in these figures we can see the results comparing to the results in the reference paper with the given parameters for the single Stokes case. We can see here, for example, 1 over lambda, when 1 over lambda increases, then optimal strategy also increases linearly in when there is no relative performance here, for example, right? And when the relative performance parameter is 1, right, which means that the group has the full impact on the agent, we can see the optimized strategy stays stable here. Okay, next we consider the homogeneous agents case. This means that all agents are homogeneous in their risk aversions and relative performances, which means that expectation of 1 over gamma is 1 over gamma, and expectation of all thetas is theta. And then with this assumption, our strategy turns out to be this strategy. And then here we give the following result here. Okay, and then we can see that when there is, for example, when the relative performance parameter is 1, right, we can see an immediate jump from 0 to something somewhere which is close to 5 here. Okay, so yeah. Also, we see that from this figure that when the group has no influence on the agent, which is theta is 0, then we have the classical Merton solution. Okay. So the next, we consider a pure jump process model where the sigma and nu are 0. The first case under this situation is when epsilon tilde is 0. With this assumption, the resulting equation turns out to be this, and then we can find this optimized strategy, right? And if we assume all t etas and epsilon heads are equal to each other, then we have a homogeneous agent assumption also here, and then we take the expectation of both sides, and then we can isolate optimal pi as given here, okay? And then we generate the results here, but for generating the results, we need to find the optimal values of the parameters. For this, we see that, and we use the fact that the well process X of the agent have the same expected return and uncertainty as in the pure diffusion case, and then we find the optimal parameters, and then we use this for generating the numerical solutions. And then here we can see for different intensities which denote the number of crashes in the market given in this set, right? We can see the optimized strategies for different number of the intensities here. And then we can see that when the number of intensities increases, the solution gets an approach actually exactly to the one as in the pure diffusion case. And also we see that for larger the jumps, we have more asymmetric return. The following figure shows actually the upward jumps, right? And then we take this a number of crashes here, and then oppositely we see that when the number of as you can see here, right, when the number of crashes here increases, right, so the strategy gets close to the one as in the pure diffusion case. And then we also observe that when lambda less than or equal to 1, the model produces an arbitrage. Okay, so yeah. So why we have seen that the model produces arbitrage? Because when lambda is 0.1, the model has no solution. But when lambda is equal to 1, we find the derivative parameter as 0, and then we see an opportunity to win when there are stocks, right? And then we see that we say that the model has the arbitrage when lambda less than or equal to 1, and the problem has no solution. The next case is when epsilon is 0. In this case, we have the this equation, and then we can obtain the optimal strategy as given here. Okay, and then by our previous results and by these results also, we see that when volatility is 0 and epsilon is 0, We have jump diffusion case, but we don't have joint risk between the agent and the group, right? And then in the formula, the relative performance parameter disappears. So theta only appears when there is joint risk, okay, which is this condition actually. The next case is when epsilon is epsilon tilde. In this case, we have this following equation. So to find a nice formula here, we suppose actually this, and then we have the homogeneous assumption, and then we take the expectation of both sides, and then we obtain this formula, but just under the case of theta is 0. But we cannot isolate optimal pi for different values of the theta. So also from here, we see that the when theta is 0, which means that there is no relative performance, the agent doesn't care about the group's performance, which makes sense actually, right? And also the risk aversion degree of the agent, which is gamma, right, always appears on the formula of optimized strategy. So when also theta is equal to 1, there is no risk aversion appearing on the formulas, right? And here in this formula, we show some results for small and market benchmark portfolios. For a small benchmark portfolio, we just insert the result for optimal solution result for the group into the formula for the agent, and for market benchmark, we insert pi hat is equal to 1 because we have this case here, right? And then we see that this result under when epsilon tilde is 0 with the given parameters. Okay, so as a conclusion, we obtained optimal strategies resulting from portfolio optimization problem under the relative performance, and we obtained the results for agent where the agent's behavior influenced by the group decisions, right? And we also saw that when the number of in our analysis, we saw that when the we can also recover our the pure diffusion case by our results in the pure jump cases, and we also say that in jump diffusion case, the model can create an arbitrage, and these are the most relevant references that you can have a better idea about this problem. Thank you very much for listening.